Hi, I'm Zixuan. I'm going to show the EE533 Lab2 demo. This project is to use the ISE to make the ALU and the adder. So I'll show what I did in the project. First I used the um, like here. First, I made one bit adder. As we can see, the X is the XOR by the AB and BC. So, and also the C out is the two end. One end is one input of the end is the output of AB XOR, and another is input is C. Uh, this end is for the AB XOR equal to 1 and then C equal to 1 and then C out will be 1. And another case is AB both of them are 1 and then the C out will be 1. So I use a 1 or at the end. And then I make it to a symbol to combine the bar bit adder. This is the carry out adder. And in the same way, I use it to create a symbol to combine a 32-bit adder. In the report, we are asked to use the flip-flop, then and combine the flip-flop to one bar-bit flip-flop. And then connect it to 16. This is 16 flip-flop and 32-bit. Oh, sorry, this is 3-bit. After that, I combine them to make the ALU 32 D flip-flop here. After that, we can make the simulation and for here, ALU 32 DI5 TB. Yes, this is the test bench, and we can make the simulation. And we can. Oh, sorry, this is ALU. I want to use the adder. It's 32. We can see here, A is I555, and the B is 11111, 81, and then as a result is 7, 1, and 1, 0. Because we use the diff flip-flop at the input and output, so the output will be shown in the next clock. Like the postage clock, we get a value of A and B, And after that, in the next positive clock, we get the output value here. So it's correct. So in the same way, the second numbers are 1, 2, 3, 4, and then the output is here. It's correct. And the in the next clock is 2 all F, and the output will be here. So you can see when you get the input and in the next clock we'll get the output. So like we change the value here, here. So we will get output here. So it's right. So we can go to the next step. The next step is to combine our ALUs and either 32 bits to make a ALU. In the ALU, I define some more, make some more functions like copy and zero detector and subtractor and one shifter. I'll show what I did. Sorry, ALU 32 here. As you can see, this is the Adder 32 bits. And if we want to use this to do a sub function, so we need to invert the input and add one. So in the design, I use the OP code, and the OP code is 3 bits. I use the lowest bits to decide if it is a sub or add, like here. This is OP0. So if the OP0 is 0, it means we will use the add. So A will be here, and B will go here, and they will add together. If the OP is 1, it means it will do the sub. So as a result, the B will go in the inverter and select by the marks, and then go the input of the adder. It inverted, and the scene will be 1 is to make the subtraction. As a result, the result will be here. It will be the adder of the sub. So this is the OP0 to control that. Also, we use I add one more shifter. The function is shift left 1 bit or shift right 1 bit. So what I did is just used one buffer to switch the ports. Like the wheels is from 0 to 30, and if it want shift right, it will be all of the wheels will add 1. So as a result, the wheel will be 1 to 31, and the LSB will be 0. So I connect the LSB with ground. In the same way, if we want a shift left of 1 bit, so we could use the highest 30 bit from 1 to 31 to 0, 30. And we add one more MSB with 0. So this is shift left, and this is shift right. And then we use the marks to the selected. Also, we use the OP0 to select if it will be shift left or shift right. And this is the output um, of the function shift. And after that, this is the copy functions. We use the OP02 to control if it's copy A or copy B. It's a bit easy to just use a mask to implement the copy. After that, I add one more uh I'll add one more function called equal. Equal if A and B are equal. I'll show what I did. Like here, and O zero means the input of A, and 1 0 means the input of the B. So all of the bits will be the XOR. Actually, we want to use it to do an XOR, and then we can use the AND to detect them. But also we can also use the XOR, just use the XOR and with the OR and check if it has a one uh, in the result. So if the two number of A and B are equal, then means all of the outputs here, all of the outputs will be zero. So as a result, the this output will also be zero. And then by one inverter, the output will be one. And in other case, if the A and B are not equal, the output, one of the output here will be one. And this output uh, will also be one. As a result, um, the result of the inverter is zero. So this is the equal function. Because our equal function is only one bit, so I use the 31 bit to make it to 32 bit at output. Also, this max is to select from equal function and with the default case. Our ALU just have 7 functions, and in the 8 1111 is the default case. The output will be zero. So I connected it to the ground. It also controlled by the OP0. And then I used the OP1 to control if this max output is either or shift. If this max output is the copy or equal or the default case. And then the max is controlled by the OP3. Yes, OP2, the third of OP. Sorry, MSB. And then we will get output. This is the structure of my ALU. And I'll show the simulation here, ALU. Like here, because we use also the D flip-flop at the input and output, so the output, the result will be uh, will be shown at the next clock. So if we OP code is 0, the output we get output here is this one. B is this one. So the output will be here. It's right. Or we can use the calculator to make the verification. And in the second clock, we get these two output, and the result will be this one, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 8. As you can see, it's correct. And then it's the same. 1, 2, 3, 4, 5, 7, 6, 8, 8, A, B, C, D, E, F, 1, 2. And the result will be here. It's the same. And then here we make the optical to sub. It's A to sub V. So the result will be minus 1, 2, 3, 4, 5. Here is correct. And then we can see that easily. It's the same, so the result will be 0. And then here, the result is here, correct. And then we do one overflow. This is the result. You could see it's the same one here. After that, we make it to OP2. OP is 2. OP is 2 is the left shift. So we can see here 0001 left shift is 2. Oh, sorry. Yes, this is a left shift. The result will be 8. We can use the 4-bit as a case. Like we have a number of 10001, and you can see this is the 1, right? This is the higher 4 bits of 1, and also the 000, like here. Uh, we said this is LSB and this is MSB. And then if we want move left, so we will delete this one number, and this 4 bits will be the lowest 4 bits. So the result will be the 8. So as a result, it will be 7, 8, and 1, 0, because this one will be move left, and the highest 4 bits will be 0. So it's correct. And this is move right. As we can see, 1 to 810 at one left, and this will be 1, 0. means 2. So it's also correct, 82. And after that, I used the copy, 4 is copy A and 5 is copy B. It's also correct. At last, I made OP6 to make the equal, check if it's equal. We can see F, all F, yes, they are equal. We'll check here they are not same. So in the next clock, the result will change. Like here, we get the value, and we show the result. Here, it will change to 0. And also, we get the result with the same. So in the next clock, we will also change the result. We get the AB, the same AB, and we get the result all 1. And we change A, so they are different now. Here, we get them. And in the next clock, it will be 0. So the equal is right. So these are all the functions of my ALU. And after that, I will show the Verilog. Also, I'll show the map, the log of map, to show how many LUTs I used. Oh, here, just I used the uh 99 flip flops and 228 LUTIs. Cause in my design, the equal cost a lot of gates, so I think maybe it's bigger. And I'll show the remember these numbers because we will do the comparison with the simple one. The flip flop is 100. Oh, sorry. In my Verilog, I didn't use the flip flop. I just used the LUTIs, so we can only remember this number, 228, to do the comparison. So I open the project Verilog here, and we don't use the calculator now. So first we can see, oh, sorry, we'll show what I did first. This is the same structure with what I did in the schematic. 00 adder and sub and shift left and shift right, copy A, copy B, and equal. And the default case is 0. And the opcode here, 3 bits. So in the test bench, I make a expect check function task to check it as a loop, so I can do the check easily. It's the same functions, and if it's not the same with the expectation, it will display the error. And this is the initial. Also, this is the clock. And then I just write the input and check the result. So here, if they are all passed, and it won't show this one display arrow in case which one. So if we test all or passed uh, all the cases, it will show this one. But if we failed, we will show more this arrow. So we can simulate it. Oh, it sticks corrupt. You can see we have only the all test passed. I remember I make we for the each function I used the 5 cases, so we have totally 35 verification for ALU. And we passed it, and then I'll show the LTIs I used. Uh, we we remember that in our schematic we used about 200, and for here, a Verilog it only used the 145 because Verilog will use the synthesis tools to reduce the gates, so it will have the less gates to implement our design. But like if we use the um we do the ALU manually, we will use more gates because we don't save some gates like sharing logic like others. So this is all the content about the E533 Lab2 demo. Thanks.